Khursid will be speaking about CMB constraints on natural inflation with gauge field production.
So I hope I'm audible. So good afternoon, everyone. First of all, I would like to thanks to the organizer to give me the opportunity to present my work. So by the way, my name is Khursid Alam. I am doing PhD at IISER Kolkata under supervision of Professor Koushik Dutta. And title of my talk is CMB constant on natural inflation with gauge field production. And this talk is based on this paper which I have written with my supervisor Professor Koushik Dutta and one of my collaborator Dr. Nurjaman. And so my talk is mostly similar to Ramkishore talk. So some of my slide is similar to him. So this is the outline of my talk. First, I will give some introduction where I will try to motivate what I'm trying to do, what I'm trying to solve. So then I will try to solve the background equation in the presence of the gauge field. Next, I will try to solve the perturbation dynamics of the inflaton field in the presence of the gauge field. Next, I will try to calculate some observable like spectral index, tensor to scalar ratio, and FNL. And last, I will conclude my talk. So first, I will give some motivation of my talk. So I will now in this slide I will talk about the problem in the standard cosmology. We know the standard cosmology contains 70% dark energy out of the total energy budget, and 25% dark matter, and 5% standard model particle. This model can explain many things. Like it can explain expansion of our universe successfully, but this problem has some issues. I will note down some issues. That one issue is horizon problem and flatness problem. We know that our universe is homogeneous and flat at especially flat at today time, but it cannot explain by the Lambda-CDM model. And also we know there is a fluctuation around the CMB temperature. It cannot also explain by the Lambda-CDM model. So to resolve all this tension, we have to introduce the inflation model. After introduce the inflation model, we can resolve all this tension. So that's why inflation is necessary. So now I will define some observable quantity like spectral index and tensor to scalar ratio. This is given by this expression, and this plot illustrates the plot illustrates the value of the NSR predicted from the theoretical predicted from different theoretical model, and as well as the different observation. This different color contour represent the NSR value, predicted NSR value from the different observation, and different solid line represent the NSR prediction from the different theoretical model. So for our case, we will consider the natural inflation model, and this for natural inflation model, NSR prediction is given by this violet solid line, and from this plot we can clearly see that this model is under tension by the NSR plane. So in my talk we will try to resolve this tension. So to do this, let's go ahead. How can I? So this is a setup we are considering where this is the Lagrangian for the inflaton field. This is the kinetic term of the gauge field, and this is the interaction term. where inflaton field is the pseudo-scalar field to preserve the parity invariant, where we will consider the inflaton field if potential of the inflaton is a natural inflation model, and I told you before this model is under tension by the NSR plane. So after introduce this coupling, can I resolve this tension? I will see. We will see some later. So after varying this action, we will get this set of equation, but I will now I will try to solve this equation under some assumption. One assumption is I will take the Coulomb gauge. If I take the Coulomb gauge, this term is 0, and another assumption I will take that is no when I will solve this gauge field equation, I will drop this term. Then that means I will neglect the inhomogeneity in the gauge field equation. So this assumption is valid because we are trying to probe that CMB scale. In CMB scale, this fluctuation is not that much. But if I see the evolution at the later time, this will start to go. Then you cannot neglect this term. Then if I take this term, then you have to use the lattice simulation, which talk about Ramkrishna Sharma. So now I will talk about the background dynamics. If I solve the background dynamics, then these two terms will drop. So then I will get this set of equation under these two assumptions. So this if you see from this inflaton background equation, there is a source term is present. This term is coming because of the presence of the gauge field, and to calculate this term we have to know the time evolution of the gauge field. So that to get this term I have to solve this equation. So from this equation you can clearly see that this mode has an exponential growth if it satisfies this condition, and if Xi is sufficiently large, then a large number of mode will be excited, and if large number of mode is excited, then source term will start to affect the background dynamics. And now I will see the time evolution of the Xi. If you see that if time goes on, your Xi increases, and if Xi increases, you can see that a large number of mode will start to excite, and this is the source term, and you can clearly see that when at the later time this source term start to dominate. Now I will now we know that slower parameter control the inflation, and you can clearly see this is the slower parameter for in the presence of the gauge field, and you can clearly see that if gauge field is present, then inflation duration of the inflation is prolonged, and if alpha addition and if I increase the value of the coupling strength, the duration of inflation is extended further, and this is the dynamics of the inflaton field, and this vertical line represents when the inflation is end, and this different star represent the 60-fold before the end of inflation. That means when the CMB mode goes outside the horizon, and you can see that the value of the inflaton field is different for the different coupling constant. That means the inflaton field touches the different part of the potential when CMB mode exits the horizon. So now I will talk about the background dynamics. Fluctuation dynamics or perturbation dynamics when in gauge field is present. So this is a scalar power spectrum. I have calculated this scalar power spectrum using this analytical expression, and you can clearly see that if gauge field is present, then small scale mode is start to increase, and if I increase the coupling constant, it also start to affect the large scale mode. So this I have done the same thing for the to calculate the tensor power spectrum. So tensor power spectrum, and I have seen the same thing. If I increase the alpha value, it start to affect the CMB mode. So if I know the scalar power spectrum and tensor power spectrum, we can calculate the observable quantity like scalar to tensor ratio and spectral index. This is the same plot. This is the same plot which I have shown before. This is the scalar power spectrum around the CMB scale, and you can clearly see that if alpha increases, your fast slope increases, and if I increase the alpha further, it slope start to decrease. That means our slope is changes if alpha value changes. So if we know the ns depend on the slope of the power spectrum. That's now this is the plot. Now we'll focus on this left plot where this different contour represent the NSR prediction from the different observation, and this is the this violet line represents when alpha is equal to 0, means natural inflation model theoretical prediction. And if let's first focus on, and different dots represent the NSR prediction for the model which I have considered. Let's first focus on this orange line. If alpha is equal to 0, when when gauge field is not there, then model is excluded. But if I increase the alpha value for certain range of alpha value, we can survive our natural inflation model. We have done the same thing for the different value of f, and you can find some range of the alpha value for which our natural inflation model could survive. So because for this case, sorry. Okay, this is the last slide. Sorry. So because there is a growth in the scalar power spectrum, so there could be produced lots of non-gaussianity, but there is we know there is upper bound on the non-gaussianity, and that's why I have to test which alpha value is allowed for the NSR plane. It is also allowed for the NSR plane and running of the spectral index, and you can clearly see that this is also allowed for the NSR plane. So this is the conclusion of my conclude slide. What I have seen, if gauge field is present, our inflation duration is prolonged, and if gauge field is there, it start to affect the small scale mode, large scale mode also. And for certain range of alpha, you can survive our natural inflation model. So thank you. If you have any question, please ask.
A nice talk. My first question still stands that you need to compute NS after taking into account the correct number of E folds. So your NS might shift even though you have put R down. Yes. Other thing that concerns me is the beginning of inflation in such a model.
This is beginning of the inflation, yes.
Yeah, because it has been fine-tuned in such a way that initially you have a slow velocity.
Yes.
But the fact that you have a large alpha, you will produce a lot of gauge field.
Yes.
It's very difficult to have inflation starting from a general condition.
Can you last what?
If you start from a general condition,
yes.
Your system would tend to become radiation dominated instead.
It will becomes radiation dominated when inflation will end.
So the initial conditions for inflation needs to be fine-tuned.
Yes.
Otherwise, so one has to understand how inflation can begin in such a model.
Yes.
So any other question? Go on.
When you are calculating the power spectrum, you are using a semi-analytical formula. You said.
Yes.
So you are calculating when the mode is just exiting the horizon, right?
Yes, just move exit the horizon.
So
At
K is equal to
H.
AH.
Yes.
Is there any possibility of super horizon growth?
No, because for this we have to calculate the full numerics. So, but I have not perturbation equation. I have not done the numeric part. But background part I have done.
Right. So you are calculating the H with the solving the Friedman equation exactly, but you are calculating. You are using this formula at K is equal to
Yes.
AH.
Yes.
I see. Okay. Thanks.
Okay, so if there is no other question, so let's again thank Khursid